Okay, we'll be going over Part A, Part 1 of Homework 1. So we are going to fit the water vapor pressure versus temperature data to the intone equation, and we're going to be using the Excel solver to do this. So minimize this. So we have our intone equation right here, our log PA minus B over C plus D, and then we have our our data over here. So first thing that we need to do is we need to make some guesses for our A, B, and C so that our solver has some values to work with. So A, B, and C, and we'll do create from selection so that we can name our right row or right column. Yeah. And then we'll go ahead and make some guesses here. Oops. Let's see. Make some guesses here. We'll say like 4, 8, and 3. Just so that we can make a model right here. And our model, we want our dependent to be P. So we'll go ahead and do 10 to the log and 10 to our right hand side right here so that we can get P by itself. So that would be equal to 10 to the A minus A dot minus or B dot, and then divided by our C dot, and then plus our T. Okay. And yeah. Sure. So we have our model, and we'll go ahead and extend it all the way down right here. Yeah. Pretty bad guess. We have 9396 right here. So we want to go ahead and find our error in here. So our error, and this will be our P minus our P model. Equal. And then we want this also to be squared. That way, if it's above 2400, it'll get added, and even if it's below and subtracted, it will be a positive either way. So we want this squared. So 2400 minus right here, and then squared, and then we'll go ahead and extend this all the way down. Okay, so too bad, and then we have our sum of errors, which we'll just want to be equal. Actually, we'll have it labeled here. Sum of error. And this will be equal to our data right here. So sum, to here. Okay, and then we are good to use our solver because we have our variables right here that we can change, and we have something that our target value that we want to minimize right here. We want to get this as close to 0 as we possibly can. That way these values have at least difference as possible. So we go to our data, go to our solver, and then that fell. Just a little more. Oh, yeah, that's good. Very low. Alright, so yeah, we have our solver right here. We have our changing variables, which we want to be H3 through R6 or 5. So right here. And then we want our set objective to be G9. And we want this to be minimized. So we go ahead and we hit solve on it. And we have this being our solver bunch that came up right here. Okay. So went down, our P model is now at 363 right here, so not too good right here. And then it does get better as you get down to the bottom because the magnitude does increase so much that these get a little bit better right here, even though the air is so much. But we just needed some air to be able to minimize this. But that is how we use the solver to do Python, and next we'll in our Excel, and next we'll move on over to Python. Well, one thing I forgot to add, this solver works by basically just iterations and also just guessing. So there's a number of solutions that could work out here, but Excel just kind of picks the best one. So it's not the most accurate way of modeling data, which is why we're going to move over to Python and explore how we can form a linear regression with our HW1 equation. So yeah, we'll do that next. Okay, so let's go over some of the math before we go into the Python about how we can change this HW1 equation into a equation that we can use in Python to model our linear regression. So we have our log 10p here equals a minus b t plus c, and we know that for linear regression we have our y model matrix right here. So our y model, and then this is equal to our design matrix of A, and then we have our constant coefficients right here. So right here would be our constant coefficients, and this would be we call this C. All right. So in order to go through this, like how to get this to here, we can look at ax squared plus bx plus c, and we can see here that and equals our y model. So we have our y model right here that we would use over there, and then we have our x squareds, our x, and we don't have a constant right here, so we would combine these into a matrix. So our x squareds would be right here. We have x squared 1, x squared, and our 2, and our x squared, and our 3, all the way down to, I'm running out of room, but it'd be xn squared. And we have our x1, x2, x3, xn, and then our c would just have one values right here. And this would be our design matrix. And then right here, we would have our constants right here. So it would just be our a, b, and c. So we can model this if we get p and t by itself, because those are two values that we know. If we can get those two together into a like if we can get t into our log 10p right here, or with our p, we can have our y model, because they're two values that we can calculate, and we won't have any unknowns in that number right there. So that's basically our goal. We want to get this y right here to have our p and t together in one set, and then we can move everything else to the right hand side. We can separate our constants and separate our p and t valuables. So we can go ahead and do that. So we have log 10p equals a minus b t plus c. So we can times t plus c right here and t plus c, so that we can combine these together. So it'd be log 10p equals a t plus ac minus b over t plus c. Okay, and then we can go ahead and multiply our t plus c over to the other side. So that's what will end up being, so times t plus c, that cancels out, and we have our times t plus c, which we can then distribute across or through, and go ahead and separate those out. So t log 10p plus our c log 10p is equal to at plus ac minus b. And then, so like I said, we wanted our y to involve calculable number. We wanted our y to be a calculable number, and with our T and P. So this right here is going to be our Y, and we want to get hit this by itself, so we'll move this over to the right hand side of the equation. So basically we have our Y model equal to our kind of box right here. This will be our right hand side of this equation. So we have T and then log 10P is equal to C log 10P or minus C log 10P, and then plus AT plus AC minus B. Okay, so we have we can go ahead and shape it into our design matrix and our coefficients right here. So we can go ahead and do that. So we have our T log 10P is equal to our minus C log 10P C log 10P. This is our A matrix, so we have negative C log 10P 1, 2, all the way to the letter N. So negative C log 10P N, and then we'll have our AT right here. So this will be AT1, AT2, and ATN. And then right here, since we don't have a T or a P, we just have ones right here. So this will be our design matrix, and this is our 1, 1, send that out. And then T2 log 10P2, and we get to our Tn log 10Pn. So this is our Y model right here. So we have our design matrix, and then we have our constants, which are just, or this should be, sorry, our constants should not be in here. That should just be A, T, and 1, 1, 1. And then our constants are in here, so we have A, C, and then A, C minus B. Okay? So we have our design matrix right there. So yeah, so we have our Y model, our design matrix, and our coefficients right here, our constant coefficients. So we can then take this to Python to use for our multilinear regression. How before in different homework we use the perpendicular to our error. If we want our design matrix to be perpendicular to our error, and we use our error Y model, or Y data minus Y model, in order to form two equations and get our unknowns. Yeah, we're gonna cut this out. Okay, so now that we have our Y model, our design matrix, and our coefficients, we can now use this in Python to use in our multilinear regression. And so we'll go ahead and move on to Python. Okay, so we're going to be going over homework 1, part 2 right here. We're going to be using the matrices that we set up to get our Antoine parameters, our coefficients, using the lineage solver, and we're going to plot the data and fit the model. So we can move on to that. So I got our imports in already, and downloads for the imports that we needed, and I also uploaded our data right here. So we're going to go ahead and get that data out. So TP data is equal to our np.gen from text, and then we have the name, so water pressure.csv, and then our delimiter is equal to set. Okay, so we can see if we have our data out or not real quick. Enter, it's the same, water, vapor, oh, I spelled. Yeah, okay, there we go. We have our temperatures right here, and we have our pressures right here. So we can go ahead and separate this out, get those out, so that we can use them further in our calculations. So we have T is equal to our, has it there for us already, so our TP data, so that's the array we want to pull it from, and we have our colon, which basically says we want this to associate with this column, and this column is 0 because the index in Python starts at 0, and then this would be the 1 index for the pressure. So again, the column, colon, and then that indicates that we want to pull out from a column, and then the index is 1, so it pulls out for these pressures right here. Okay, so we can go ahead and see, actually shift enter, get that away. Okay, so next thing we're going to do is we're going to set up our design matrix. So we have A is equal to our np.c. We want to set up columns, columns, and then we have our T data in there. And then we have our negative np dot log 10 or 10, and then we have our P in there, capital P, and then we want our ones, so we want np dot ones underscore like, and then we can just use our T variable to get how many ones we need, because we want to match the amount of T's values in our array. Okay, and we can go ahead and see if that worked. np, oh, that should be dot. Bad. T equals np.c. Oh, I need brackets. That's what I need. It's an array. Shift enter. There we go. Okay, so we have our temperature, we have our negative np log 10, and we have our ones. So the next thing we need to do is set up our Y model array. So we can go ahead and set up Y model is equal to our, or yeah, we can just go ahead and do that. So model is equal to what was it? It was the left hand side. So T times np dot log 10, and then P. Or that should be a capital P. Okay, we enter, and we have our Y, or not Y model, Y data. Call that Y data. Or yeah. Let's call it our Y. We'll just call it our Y. And then shift enter. So that gives us our array of all of our known values. So we can then use this to do our lineage solver. We'll use our design matrix transpose times our Y model, and then we'll use our AT transpose times our design matrix. And we know this because from our error we know that it's Y data minus Y model, and if we plug in our Y model with our Y data, we will get our AT transposed times our Y, and then our AT transposed times our our design matrix times our coefficients, and so our lineage will solve for our coefficients. So we can go ahead and do that. So shift enter, and we'll go ahead and separate these out too. So we have our A, C, and then our A times, or let's do ACB, and then that's our A times C minus B coefficient, and then we can do np dot lin alg dot solve, and then we have our A dot T times A, or it went away. So at, and then our A, and then our A dot T at Y. Okay, and then we can go ahead and hit shift enter on that, and then, or I guess we can see if we pull it out right. So A, shift enter, that's our float. C, shift enter, and we have our ACB. Shift Shift enter. Okay, so obviously we need to pull out our b valuable or our b constant value. The way we can do that is we can set up a times c minus b equals x, since x is the constant and we know a and c. So we can do a, we can do b equals a times c times c, and then minus x, which is the constant, so a, c, b. And then b, shift enter, and that's our value for b. Okay, and the next thing we'll do is we'll move on to plugging it back into our cell and seeing our difference there, and then we'll make a graph for it and see the result. Okay, so actually we don't have to go through the Excel, we just gotta graph it on Python and compare it to the, or let's see what we get. We just have to plot the data and the fitted model, and we'll use the log learning scale for the y-axis. So we'll go ahead and do that. Alright, so the first thing we want to do though is we want to fit our data like evenly spaced. So we'll use different temperatures to plot it to make sure that there's no air in between the given temperatures. So we'll do that. So that'll be T model is equal to np dot win space. Then we want our T dot min and our T dot max, and then we'll do it. And then this is how many times we'll evenly split the numbers in between our T min and T max. Oh, I forgot though. So this is how we'll split the numbers up. We'll just do 200, shift enter, or not shift enter, we'll just hit enter on it. And then we'll hit, yeah, we don't want that. We'll hit fig equals make underscore subplots. And then we'll do fig dot add underscore scatter, and we want our first plot to be x equals t, then y is equal to p, and our mode, we want markers because this is our data, and we'll say this is our name equals actual data. Okay, and then we'll add our line, so fig dot add underscore scatter. We want our x to equal our t model. X is equal to our t model, and then we want our y to equal our Antoine equation solved for pressure, so 10 squared. Then we have our a minus our b, and then we want this divided by our t model, and then plus our c. And then we'll put one more on there just to make sure it's really getting the right answers. Okay, and then we have our mode is equal to lines, and then we want our name to be we'll just call it model, or I forgot the equal. Let's say model line. Okay, and then we'll go ahead, and it said it wanted our y-axis in logarithmic, so we'll go ahead and do that. So fig dot update underscore y axis and type log. Okay, and then we can go ahead and do fig dot show. Shift enter. Oh, P is not defined. I didn't do capital P. Capital P. Shift enter. That does not look right. So hold on 1 second. Okay, so I realized that I have the A minus B here and not the A minus B over T model plus C. So I'll go ahead and fix that. That is no bueno. So B, and then I need another parentheses right here, and this should do it. Okay, yeah. So we have a basically like almost perfect model right here. So yeah, that's it for the Python. We used our linear algebra and our matrices transpose to solve for our coefficients, and we made a model based off our data. So that's it for the Python.